Hello, everyone. Thank you for tuning into my presentation. Today, I'm going to be talking about my project on designing self-powering mats for use in room-level localization and occupancy detection. I did this project with Professor Richard Howard and my advisor, Professor Marco Grutesser. My name is Minitha, and we're affiliated with WinLab Rutgers University. There are many uses of knowing where people are in a building and how many people are present in a room. For example, it could be used in residences for things like automatic light shut-off or intelligent HVAC, or in commercial settings for location-based business analytics. Indoor positioning systems could locate people in places where GPS tends to fail. Typically, you would want these systems to be device free so that people don't need to be holding a device in order to be detected. There are some systems that use existing devices in a room, like surrounding smartphones or Wi Fi APs. And there are also some systems that have dedicated instruments that are installed for sensing. Uh, Typically, these systems use a particular kind of signal like RF, ultrasound. Commonly, these three kinds, RF, ultrasound, or IR, they also can use environmental signals like light, sound, or temperature. And by using techniques like RSS analysis, fingerprinting, neural network learning, it's possible to detect the presence of a person by using the changes in the signal that their presence would bring about. Using these kinds of wireless indoor positioning techniques has some drawbacks. Since we rely on the signal strength across an air channel, which is a highly varying channel, multipath effects and noise can affect the accuracy of detection. Modifying and installing either existing devices or dedicated sensing instruments can be tedious and expensive. These sensing devices would need to be powered either through the electrical mains, so wiring and dedicated power conversion would be needed. Otherwise, batteries would be used for powering, which in turn would require replacement when they run out. There is also the current consumption of these sensors and transmitters. They tend they tend to be in idle mode when they're low power, where they draw microamps while in idle mode, and occasionally they pole and transmit. And while they do that, they draw tens of milliamps. So the event of a person passing by is a quick event. It needs to be detected. Since that needs to be detected, the device needs to pole often, at least a couple of times a second. And these systems consume a lot of unnecessary energy for detecting people, since there's not going to be people walking around a lot of times. So there has to be some kind of way to have a system that does measurements only when needed, drawing that higher amount of polling energy during the event only when the event happens. Additionally, instead of consuming more power, it would be beneficial to have the event of a person being present power the entire system so that there wouldn't be the need for dedicated power for the sensing devices. So, in that vein, self powering low energy devices seems to work out for the present day needs to cut down energy and reduce current draw. That brought us to piezoelectric devices. Piezos offer a path to both power and sense using the same device by converting the mechanical energy that a person expels to electrical energy. Since piezos generate an electric charge in response to a mechanical stress, this charge is also proportional to the amount of force applied on the piezo. So if we were to put these piezos on the floor, we thought we might be able to get information and power to power the circuitry using a person's footstep. So knowing where and in what direction a person's footstep is can provide useful tracking information of the person and do room level localization. So that brings us to the problem statement. We check if it's possible to design a floor mat that could be placed in front of doors for tracking people flowing in and out of a room to do occupancy counting and room level localization in a building. We see if it would be possible to power itself when it is stepped on, and if it could detect the direction that a person is walking in. Now let's take a look at a high-level overview of the system we're trying to design. We take a floor mat which has piezoelectric devices or piezos embedded in it. When a person that we want to detect steps over the mat, the person exerts hundreds of newtons on the piezos. The piezos convert that mechanical energy to electrical energy. This electrical energy, which is in the form of a voltage waveform, would be able to power a transmitter. This transmitter could send a packet of specific characteristics of the waveform that correspond to characteristics of the footstep. And this packet would then be transmitted to a server for further processing. This seems like a bit of a long shot. Thankfully, using piezos to power transmitters has been done before, and there's some related work that we can turn to. The HSR Vote battery-free device was developed in 2019, and it's a classroom response system like a clicker, but it takes its energy from the click itself by using piezoelectric buttons. There is some circuitry, and upon pressing a wireless telegram with data of which of these four buttons were pressed will be sent to the teacher's computer, and this system and other wireless batteryless battery-free push-button transmitters require a deliberate push from the user, contrary to our device-free approach here. Even more similar to our work are smart tiles, which have custom-made piezoelectric sensors in them that power a wireless transmitter when a person steps on the tile. And that transmitter signals like a light bulb or like a fan to turn on depending on whether the person stepped on the tile or not. So these tiles, they have custom-made piezos that are made for this particular application, and there is no direction detection. It's mostly based off of whether the person stepped on the tile or off of it. And these projects, they serve as additional evidence that it would be possible to power a transmitter from the energy of piezos. That brings us to our prototype design for our self-powering floor mat. We check whether it is feasible to use off-the-shelf piezoelectric sensors instead of custom-made ones in self-powered floor-based sensing designs. And we see if it's possible to create a precise mechanical setup to embed such sensors into a floor mat design. Because piezoelectric sensors are known for producing very low amounts of energy, and we want to be able to get as much energy as possible out of them through a very good mechanical structure. Then we see whether we can use the waveforms that come out of those piezoelectric sensors to get specific information about the direction of a person walking over the floor mat from the differences in piezo activation or other factors from the piezo waveform so that we can get estimations of room level occupancy. To talk about the design of the setup, first we'll go through a very brief description of how the piezoelectric device works and which one we selected. That is the element in the mat that would be converting the mechanical energy of the footstep to electrical energy. The piezo that we chose was the PZT diaphragm piezo. It is a very commonly used piezo, low cost of around 30 to 40 cents per piezo. It has a really good structure that we found very useful for this particular project. PZT is known to be brittle, and it stands for lead zirconate titanate. There are better piezos out there, but for this project, we wanted to stick to something that is commonly used and off the shelf. So how this works, just for an example, this is an example voltage waveform from the output of the piezo. So on the left, if there's an applied force on the center of the piezo, it flexes and bends and gives that gives rise to charge accumulation, which gives rise to the voltage waveform that you see. So when the force is applied, that results in a change in displacement, and as long as there is a change in displacement, there will be a voltage increase or a decrease in the negative direction. One of the advantages of piezos is their precision, their voltage to displacement of the center of the piezo. Those graphs have little room for error, which is why they are used in even actuators for making nanometer displacements. They're very precise. In order to leverage this precise sensor, we have to make a rigid setup that will keep the rim of the piezo held down so that the center can move up and down when force is applied on it, which would cause a displacement of the center. In order for all of the force from the footstep to be concentrated on that center, we have a hard rubber stopper on it. And the piezo would only need to move about 1 millimeter to produce hundreds of volts. The next part of the system is the low power transmitter that we use, which is called the PIP tag. The PIP tag has an onboard MSP430 on it, which serves as the microcontroller, and it has a CC1150 RF transmitter on it. And it uses a very low amount of power, around 47 microjoules, to transmit one packet. It consumes half of a microamp at 3.3 volts while it's asleep, and it wakes up a couple of times a second and consumes 8 milliamps for 100 microseconds. So very low amount of energy. There are lower power transmitters. This is the one that we were able to get our hands on the quickest. Its range is 50 to 75 meters indoors. And the PIP tag works off of 3.3 volts. So the piezo puts out hundreds of volts. There's definitely going to need to be some conditioning there, which we'll see next. This is the circuitry connected to the output of the piezo. As we saw before, the waveform coming out of the piezo after a footstep has both the negative and the positive waveforms, and is typically over that 3.3 volts limit of the transmitter. So there are various stages of electronic conditioning that we put the waveform through, trying not to lose too much of the piezo's limited microjoules amount of energy. The first stage is the rectification stage. We use fast response low voltage drop diodes, specifically Schottky diodes, and this flips the negative cycle to positive. Next is the storage. We use capacitors with low leakage currents to stretch the energy availability over a longer duration and to conserve some residual energy that could be present from previous footsteps. These two stages are pretty common in piezoelectric energy harvesting, and they are not novel. Then comes the regulation stage. The transmitter can only accept up to 3.3 volts. So we have a Zener diode that clips the voltage at the Zener voltage when it is placed in reverse bias, and it passes all of the current through. So if we put a Zener diode of 3.3 volts or something less than that, it can clip the voltage. Next, something that's optional and that we've chosen to include in the design, even though we haven't experimented with it, is a step-down audio transformer. It is chosen to reduce the voltage and increase the current obtained out of the piezo with very low energy loss. And this transformer accepts a large range of frequencies and also lowers the output impedance of the piezo. Part of the energy also goes to the analog to digital converter of the microcontroller. So we would want to record some parts of the waveform that comes out of the piezo to get some characteristics of the footsteps. So we would need to condition the waveform right after the rectification stage. We scale it down with a voltage divider before it goes to the analog to digital converter. One question that needs to be answered early on is whether the energy from the piezo is enough to transmit a packet from the low power transmitter. This is a diagram that shows how much energy is needed for each process that the transmitter undergoes while turning on up to the radio broadcast of the packet. And as you can see, most of the energy, that is 32.83 microjoules of energy, is expended on transmitting the packet of the total 46 to 47 microjoules that's needed. This graph shows the amount of energy that's obtained at the output of the rectification stage, that is after the Schottky diodes. And you can see that even a really small amount of force, 50 newtons, can be used to provide, is enough to provide that 50 joules that's needed to send a packet. In fact, according to studies, the body weight of adults typically ranges from around 46 kg to 125 kg, and that equates to around 450 newtons to 1226 newtons of force acting on the floor from a person's body weight. So the lower bound of this force is theoretically more than enough to be exerted on the piezo to transmit one packet from a low power transmitter. Now that we've covered the design of the prototype, we move on to the two floor mat designs we propose and evaluate elements of. These two designs, the single surface design and the stripe design, use the same prototype parts that we discussed before, but they differ in their placement of piezos on the mat and the algorithm and logic that they use for detection. For both of these designs, we try to exploit the typical way humans walk by lifting parts of their feet before the others. Typically, a heel strike happens before the toes settle down on the floor, and that is followed by a heel rise, by the heel rising until the toes lift off. So we hypothesize that by using multiple piezos on the floor mat, we could use the temporal differences in piezo activation by seeing which piezos get activated first and saying that those are closer to the heel, while the piezos closer to the toes would be activated a little bit later. For the single surface design, we try to map out in time where on the floor mat these different strikes happened. We could do this by having a piezo on each corner of the mat, and if we're able to use the piezo's voltage waveform to extrapolate the distance of each piezo from the point in which the force happened, we could do triangulation or trilateration and pinpoint where exactly the force happened. So to do this, we should be able to estimate the distance of the force from the distance of the point of impact of the force from each piezo from some characteristic of their voltage waveform. Next, we move on to the striped design, which is a more coarse-grained version of the previous design, where each piezo accommodates one strip along the length of the mat, and wherever a person steps on that strip, that piezo is activated. So by using a pre-known order of piezos, if a person walks in a particular direction, by using the order in which those piezos are activated, it would be possible to detect the direction that person walked in. To see whether or not we can extrapolate distance from the output waveforms of the piezos, we do some evaluation where we try to do some control measurements on those piezos. First, we use a pine wood board to press onto a piezo with a plastic stopper, as seen in the first image. Then we hang a 20-pound dumbbell at different distances from the piezo with the pine board elevated using two tables. and the other end of the pine board would be rendered immobile with a large weight. The dumbbell is hung by using an elastic cord, so it can well emulate a footstep, which is soft and rounded, unlike a sharp impact. We get some pretty interesting results. On the screen are the waveforms that we got from the output of the piezo. So this is two instances, two different trials. The piezo the weight was hung 8 inches away from the piezo both times. So the top waveforms are the direct voltage out of the piezo, and as you can see for both trials, the positive peak for the first one was 56 volts, but the positive peak for the second one was 73.2 volts. So there wasn't really a match for both trials as for the voltage levels for both the positive peaks and the negative peaks. However, since the distances were the same for both trials, the forces on the piezo was the same. So the amount of charge accumulated by the piezo would have been the same. And we find that the area under the curve for both trials ends up being similar. And we do 20 trials for different distances, and we find that the area under the curve, which corresponds to the charge accumulated, since the area under the curve would be V times T, which is proportional to current times T, which is the charge, that ends up being the same for the same distance from the piezo. This graph shows 20 different trials for 5 different distances of force exerted on the piezo versus area under the curve. So it's a scatter plot, and as you can see, there is enough variation and enough sort of correlation between how much area under the curve you would see from the voltage waveform of the output of the piezo versus the distance the force was applied. To evaluate whether the stripe design is feasible, we use a floor mat and we use some piezos that are connected to an oscilloscope. So the piezos are raised from the ground with two parallel metal strips, and they are insulated from those metal strips with electrically insulating epoxy so that they're not shorted together. And perpendicular to this are three overhanging longer metal strips with plastic stoppers that would rest above the centers of the piezo. And that entire setup is it's placed under that floor mat. The voltage waveforms are monitored on the oscilloscope, and the experimenter they cross over and step on the mat barefoot 10 times. And what we do is we have the trigger on the oscilloscope, and we have a low resolution of around 20 milliseconds per division. And for all the 10 trials, what we saw was that step resulted in some temporal differences in when the waveform started and started from zero. So this is an indication that you could possibly determine the direction, since the piezo that activated first was the one that was closer to the heel. In conclusion, we show that there is a way to integrate energy harvesting and pressure sensing so that we can wake up and power sensor nodes on demand when an event occurs. We also show that it's possible to design a piezo-powered floor mat that can detect footsteps and the direction of walking, and these can be placed at entrances to support room level occupancy detection and localization. We also conduct some preliminary experiments that show that a good amount of energy, 200 microjoules, can be harvested from a footstep, which is sufficient to power most low power transmitters, ultra low power transmitters. And that suggests that footsteps and walking direction detection is feasible. Thank you very much for listening to my project.